Alright, so we'll go to the concept 2 called the Fleming right hand rule. Okay, so before I go to Fleming right hand rule, let us recap on what we have learned. Right, so the first rule that we have learned is the right hand grip rule, which tells us the direction of a magnetic field. Okay, so my current is moving. I can know the direction of the magnetic field using right hand grip rule. Okay, next will be my Fleming left hand rule. Fleming left hand rule tells us the direction of the force acting on the wire, and this wire must be carrying current. Okay, so just remember your F, your B, and your I. Okay, so your current is flowing in this particular direction, and the magnetic field is in this direction. Okay, so if you use your Fleming left hand rule, you will determine that your thumb will be pointing downwards. Okay, so this will be the direction of the force. Okay, so next will be the Fleming right hand rule. So Fleming right hand rule tells us the direction of the induced current when a metal rod moves through a magnetic field. Because when your metal rod cuts the magnetic field, this will cause induced EMF inside the wire. Note that this wire is not connected to any battery. Alright, so it's just cutting through. Yeah, I use my hand to cut through. Right, so this process will cause a current to flow through this so-called wire or metal. Okay, maybe I use metal. Right, so using the idea of Fleming right hand rule where your thumb is the motion, right? So normally I will just use FBI again. Okay, because when I apply a force onto an object, normally the object will move in the direction of the force. Okay, so I just put F, then B is your index finger, and middle finger will be your current. Okay, so notice that this metal rod is moving towards the right, and the magnetic field is into the paper. Okay, so if you point correctly, your middle finger should be pointing in this particular direction. So the current is moving from this point, okay, to this particular point. Alright, so if I connect a so-called circuit, yeah, the current will flow in this particular manner. Right? Okay, so of course the lamp will light up. Okay, so the next thing, I think this will be tested more in school exam rather than O-level. Alright, so the next thing they'll ask is that which point, let's just say this is point A and this is point B. Okay, so which point is the positive, is positive and which point is negative. Okay, so we know that the current flows from high potential to low potential, right? So they'll ask you, is point A or point B higher potential? Okay, so if we use the idea of the current flowing from high potential to low potential, we will get the wrong result. Okay, because you must treat this metal rod as the internal of a battery. Okay, so internal, so let's just say you have an internal of battery. This is positive and this is negative. Okay, so when I say current flows from high potential to lower potential, I'm talking about the external of a battery. Right, so this is your battery, so let's just say put a current here, and the current flows from here, right? Flows from the so-called higher potential to lower potential. But for this metal rod, I must treat it as the internal of a battery. Okay, so internal of a battery, basically your current is flowing from negative to positive. Okay, so this metal wire, the point A will be negative potential, while point B will be higher potential. Alright, so treat this as the internal of a battery. Okay, likewise for your solenoid, treat it as the internal of your magnet. Okay, yeah. So there's another way of seeing whether which point is high potential and which point is lower potential. Okay, so this is the same rod, metal rod A, maybe here, A, and point B, right? Okay, and this metal rod inside got many free moving electrons, and this metal rod is moving in this particular direction. Okay, so for this, just take this as a number of electrons moving in this particular direction. Okay, yeah, so all these electrons are moving towards the right. Okay, so if you remember your Fleming left hand rule, okay, FBI, so Fleming left hand rule can tell us the direction of the charged particle moving inside a magnetic field, right? So you use your Fleming left hand rule, your magnetic field is into the paper, your current, so your middle finger is your current, right? And notice that my middle finger current is the conventional current. Okay, so your middle finger must be pointing in this particular direction, because electron is the flow of electron. This is not the induced current. I mean, this is not the current. This is not conventional current. Okay, not conventional current. Okay, what we want is the conventional current. So if your electron is moving towards the right, your conventional current is moving towards your left. That's why you need to point your middle finger towards the left. Okay, so notice that there's your electron will experience a force. Okay, so let's just say I draw electron here. Your electron will all experience a force in this particular direction. Okay. Right. Okay, and it's moving in this direction. Okay, so of course it will undergo so-called a circular motion, so your electron will move in such a direction. Okay, let me draw the magnetic field. Okay, so after some time, when you push your metal rod for some time, this metal rod, all the electrons will accumulate in this place. Okay, so okay, so after some time, all your electrons will accumulate in this particular place. Okay, and there's an absence of electron on the top of the rod. Yeah, so the absence of electrons means it is positive. Okay, and the presence of all the electrons at the bottom of the rod means that at this particular point or region, it is negative. Okay, so you can also use Fleming left hand rule to determine which point is positive or higher potential and which point is lower potential by using Fleming left hand rule. Alright.